Let's continue to the unit step response and time domain specification now. The transient response of a control system is necessarily important because, as I said before, both the amplitude and the time duration of the transient response must be kept within tolerable or prescribed limits. Okay. For example, yt, which is output for any system, and t. You want from the system to goes to this reference signal, okay, which is r times ust, as you see. But your system reacts as like that. As you see here, we have some exceed the reference value, and also, as you see here, at this time we provide the steady state, but this time is important for us. For example, we want from the system it should be here, okay, or maybe you want from the system it should be as like that. Okay, so it's about the transient response of the system. For linear control system, the characterization of the transient response is often done by use of the unit step function as the input. Okay. For the second order system, or for any system, maybe we can write the specification on a graph, which is bigger than the last one, t and yt. This is the reference signal, for example, 1. We have a band here, 1.05, 0.95. We have a band here. How the system reacts, let's draw it now. For example, the system reacts as like that. Okay, this is the reference signal, as you see. Maybe we can draw it different color. As you see here, we have a difference between the reference and overshoot. It called as maximum overshoot. At this point, assume that the time is t max. So t max represents the time in maximum overshoot value. Okay. What about more? The system, this point 0.1 and this point 0.9, this point 0.5, this time range called as rise time. Which represented by TR. And this time range called as delay time. Delay time, and it represented by TD. Maybe we should show also this point 0.6, 3 and 2. Okay, maybe we can show it with different color again. This time range, as you know before, called as tau. Tau means time constant of the system. Okay, what's more, as you see here, we have a band, and it is accepted as 5%. The final value should be 1, and this band will be 0.95 and 1.05. So we have 5% band here. Okay, for this point to the horizontal axis, called as TSS. It's mean, sorry, TS only. It's mean settling time. Settling time is defined as the time required for the step response to decrease and stay within a specified percentage of its final value. Okay, a frequently used figure is 5%. It may be 2%, so it will be 1.02 and 0.98. Okay, but in here, as an example, we assume that it will be 5%. So this signal is going into this band, and it should be here after this time. So this point will be settling time for us. Maybe we can express them mathematically. We can start from the maximum overshot. Maybe it called as PO, peak overshot. If this signal is like that, what is the settling time now? As you see here, now it will be the settling time, TS1. Okay, the signal will goes into the band and stay within in this band. Let YT be the unit step response. So the maximum value will be Y max T. And in here we have an assuming Y max, of course, greater than and equal YSS. YSS means steady state value of the output. Okay, for example, in here we can say this is the YSS value. So the maximum overshot or PO will be Y max minus YSS. It is usually accepted as not steady state reference value actually. But here in your lecture notes, YSS. For linear control system, the characterization of the transient response is often done by use of the unit step function. What is the maximum overshot value? It can be always used as a percentage value. So percentage PO will be maximum overshot divided by YSS times with 100. So the result will be percentage value. The maximum overshoot is often used to measure the relative stability of a control system. A system with a large overshoot is usually undesirable behavior. Okay, it's important. We always want from the system a minimum overshoot value. For some system, the maximum overshoot may occur at a later peak, and if the system transfer function has an odd number of zeros in the right half-S plane, a negative undershoot may even occur. Okay, what is the second one? Delay time. Delay time is defined as the time required for the step response to reach 50% of the final value. 50% of the final value. What about rise time? Rise time required for 10% to 9%, okay, of its final value. And represented with TR. As you know, delay time is TD. And the other one, settling time. Maybe we should write it in expanded version. The settling time is defined as the time required for step response to decrease and stay within a specified percentage of its final value. The specified percentage value is usually 5%. But as I said before, it can be changed. It can be, for example, 2% or 1%, okay? But usually this value is 5. And the last one for the transient response, steady state error. Okay, what is mean of steady state? We forgot it on here. For example, the last value of this system is like that. So as you see here, we have a difference. Again, as you see here, we have a difference between the input and the final value of the system. Okay, this difference called as steady state error. Steady state error. So we can say easily a difference between the final value of the system and input signal or reference signal. It is called as steady state error. The first 4 quantities give a direct measure of the transient characteristics of a control system in terms of the unit step response. These time domain specifications are relatively easy to measure when the step response is well defined. But analytically, these quantities are difficult to establish except for simple systems lower than the third order. Okay. We will do some approximation to calculate them, and we will give some equations to calculate them, but we should remember that we have some assumptions to calculate all of these values.